Making Math Easy. And today, we're going to talk about an experiment that not necessarily proves, but tests the law of conservation of energy. Energy is a property that matter has. You might have heard of energy before as energy that nutrients give you. But that kind of energy is different than the energy we consider in physics. Energy is measured in joules. A joule is basically the units for force times distance. So sometimes it is known as Newton meters or kilogram meters squared per second squared. But energy has different kinds. Work is the kind of energy that happens when you push something with a force over a certain displacement. To find the work done, you measure the force you applied in newtons by the displacement in meters, which explains why the joule is a kilogram meter squared per second squared. But the two types of energy we're really going to be talking about aren't work or how fast you can do work, which is called power, but instead it's going to be about two types of energy, potential energy and kinetic energy. Potential energy is the energy that an object possesses at a certain height. Now, as you can see on this laptop, we have measured the mass of the ball to be about 40 grams, which has two significant figures, but we'll talk about significant figures in a different episode. For now, just bear with me that there are two significant figures. Now, in physics, the base unit for mass isn't grams. In terms of the International System of Units, grams isn't even the base unit either. The base unit for mass in the International Unit System is a kilogram. So, 40 grams divided by 1,000 turns into 0.040 kilograms. We added that extra zero so you can note that it's significant. Remember that trailing zeros are only significant if there's a decimal point inscribed in the number. If not, only the trailing zeros are not significant. And digits that are non-zero are always significant. We'll talk about significant digits in another episode, as I already said. But we're wasting time, so let's just keep moving. Now, we had to measure the height of the table and the height of the top of the ramp. Now, this might seem like it's wasting a bunch of work, but it's not, because potential energy includes height in the equation. The equation for height is mgh, which is the mass of the ball times the acceleration due to gravity in meters per second, and the height above sea level that it's on. So we've measured the height of the table to be 0.762 meters. If you're not used to that, I'll put it in another way, that is the same as 76.2 centimeters. And for anyone who lives in the United States, it's the same as 30 inches. So, and we also have a ramp of 1.2319 meters, or about 40 or so inches, closer to 50. 48.5, but whatever happens, we need to know the height, the gravitational acceleration due to gravity, and the mass. And in the equation, mass is in kilograms, acceleration is in meters per second squared, and height is in meters. And if you work it out, and if you just work out with the units, you get joules as well. And the same goes with kinetic energy. But we'll look at that energy later. So, see, but mass and height really are the variables that if they change the entire say like 1 kilogram, it would actually have quite a bit more mass. Actually, it would end up having about 25 times more potential energy. However, if it was twice as high, then it would have twice as much potential energy. Okay, why do we care? Well, it's because potential energy is sometimes turned into a kinetic energy. And the law of conservation of energy says that energy cannot be lost or destroyed, or neither can it be destroyed or created. So no potential energy would somehow appear as it's moving down the ramp. Basically because the height is always going down and the mass can't change, or else it wouldn't be an intrinsic property that it is. Now, why bother about all that? Because kinetic energy also uses another factor, the velocity. So, given the ball is traveling at 1 meter per second, it would have a kinetic energy of about 0.02 joules, or 2/100th of a joule. But why? What's the equation that holds us on this? You might think mass times velocity and take that entire product and divide it by 2. Or in this case, some of you might be thinking that it's mass divided by 2. But that is wrong. So now let's say it's moving twice as fast, say because I pushed it down on the way, and it now goes to 2 meters a second. Now our mass would actually be 0.08 joules. Why? That's because the equation is mass times velocity, or in other words, velocity squared. So square the velocity, multiply that by mass, and take that entire product you just got and divide it by 2 to get the total kinetic energy. Okay, so, and objects of different mass, despite landing at the same time, one has more kinetic energy, assuming that they're accelerating at the same rate. If they have the same velocity as they fall down, they must land at the same time. However, this ball has more mass than this one. Now, we're assuming that this ball has more mass than this one. Despite the same velocity, the mass is what changes the kinetic energy. The bigger ball has more kinetic energy because of its higher mass. Now, okay, so now we know the formulas for kinetic and potential energy. But what's this experiment all about? We're going to start the ball at the top of this ramp and let it fall down and measure where precisely it landed. That point is what we put on this row of the table. Now the data is in inches, since this is a 25-foot measuring tape where every tick is 1 inch. So, of course, if you live in the United States, I'll just point out the number in inches. But if you don't, we are going to convert this to meters so that we can get data that we can then turn into potential energy, Okay. Sorry, I've got to look for the ball for a second. Ball, you're always hiding somewhere. Ha, gotcha. But now for this, I will need an assistant. And I already know just the assistant for the job. Assistant Jemima. Okay, that's a terrible name, but who cares? What you will do is you will very carefully, and I'll try to get on the spike part, we will very carefully drop this on here and it'll fall. I'm going to be at the ruler stick looking for where it fell and pointing out where it fell so I can shout it out in in both inches, in both inches, and convert to meters so that both USA citizens and non-American citizens are all happy.
Do I start? Do I do it?
Yes.
Okay.
I will be looking for where it landed, and you've got to be very careful not to hit yourself with that spike. There's always a blooper in every video. There's always a blooper in every video of Making Math Easy.
I'm about to do it.
Okay.
Do I do it?
Yes. That was about 3 feet.
And it moved. The thing moved.
Yes, but that was about 3 feet. Now 3 feet, we're going to write that down in our data for a second. So we have 3 feet as our first trial. Now 3 feet is the same as 36 inches, and if you're a USA citizen, you certainly know that. And if you don't, if you are given feet and you want to convert to inches, then just multiply the number of feet by 12 and you'll have inches. Now we'll go from inches to centimeters, and then go from there and divide by 100. And surprisingly, we get 0.9144 meters, or 91.44 centimeters. And if that isn't surprising enough, that is basically the same length as a yard. We need 5 of these trials. So we will do a second attempt. Assistant Jemiah?
Hut!
Okay, so again, like the last attempt, we will record where the ball landed on the meter stick and find the distance from the edge of the table.
Do I start?
Yes. That was about
I swapped it.
43.5 inches. So we'll write that down so we have a basis. Now, 43.5 times the 2.54 will give us 110.49 centimeters. But we need to convert that to meters, so that gives us 1.1049 meters. Again, if you're an American citizen, remember, that is literally the same as 43.5 inches. So this is our second trial, but we need 3 more. Assistant Jemiah? Okay, this is our 3rd out of 5 trials, and then we will average things out so we can find an average potential energy. Note, the potential energy and kinetic energy at each point is always the same. It's just the velocity at which the velocity is different. And there are reasons for that.
But we'll say it after.
We'll explain after.
Yeah. Okay.
We'll explain what's going on.
Can I do it now?
Yes. So that was about 40 inches. 40 inches multiplying by 2.54 gives us 101.6 centimeters. Or dividing by 100, you get 1.016 meters. By the way, when we average things out, we want to use our least precise measurements. And if we go back up, we had 2 significant figures here. We had 1.2319 meters, that is 5 significant digits. Here we have only 3. So we're going to round to 2, so we can do the least precise. Okay. Now we still need 2 more trials. Assistant?
Okay.
We still have 2 more trials, and after this, I can finally explain what's going on with this conservation.
Do I do it?
Yep. That was at basically 3 feet once more. And as we've already seen, that is 1 yard. Okay. 5th trial. Note that maybe this might not be at exactly 1 yard. And sometimes, depending on the different of their measurement equipment, we call that an uncertain digit. And we'll talk more about these in our chemistry and physics series, because really, chemistry and physics are almost all about units, sig figs, unit conversions, and measurements. They're ongoing the entire time. Now this is our last trial, and we'll see, does this get to a yard, or is it able to even get to 1.5 meters? We'll see.
Do it.
Yep.
Doing it in 3, 2, 1.
Once more, we're at 38 inches. We're locked up at 38 inches for a U.S. citizen. And then, doing our handy little conversion, we get 0.9652 meters, or if you're unfamiliar with this kind of 0.something meters, you get 0.9652. Now, in this table, we've already included this m in parentheses, which indicates that anyone reading the table would know that this is meters. If you see some unit symbol inside parentheses in a graph, you know that the number they have is just the number of that unit. So we can delete all these m's since the graph already says, and we'll already know that we've collected them in meters, which actually would have saved us a bit of time, but I put meters just to clarify things a bit.
Boss,
Okay,
here you go.
let me explain exactly what is going on. This 40-gram ball is losing potential energy as it goes down the ramp, but gaining kinetic energy as it goes down because of the acceleration. And the acceleration means the kinetic energy, although it's not growing. Actually, let me tell you something interesting. If some object is speeding up, there's one crazy fact that pops out. Because of the way the kinetic energy formula is managed, when something is accelerating at a linear rate, the kinetic energy grows exponentially. This is because velocity is being squared. But as it gains more and more kinetic energy, in which case, if it's accelerating at some constant rate, then as it falls, the kinetic energy is increasing exponentially. Okay, but wait a minute. What happens when it goes here? Now we can use kinematics. If we knew the velocity, then we can do something. Let's go back up and look at our data for the height. We can do 0.04, the mass of the ball in kilograms, multiply that by 9.8, the acceleration due to gravity in meters per second, take that and multiply it by 1.2319 to get that the ball has about 0.482948 joules of energy at the top. Or, again, rounding to two significant figures, 0.48 joules of energy at the top of the ramp. But what happens if we now take the height when it's on this part? At that point, the height is the same as the height of the table, which we measured to be 0.762. Now, 0.762 multiplied by the mass, the 9.8, gives us 0.29, or to two significant figures, 0.30. Taking 0.48 minus 0.3 gives us that 0.18 joules of energy has been transformed into kinetic energy. Therefore, multiplying by 2 and dividing by 0.04 and then taking the square root means that given that there are 9 meters per second is the velocity squared, we can determine the ball must have been moving at 3 meters per second at the end. And using kinematics, we can predict how far away from this, and then using that information, we can predict where, on average, it will land. What happens here is that given that we have a velocity of 3 disregard that term from the formula shown on my left. So we can then cancel out the velocity, and we're left with the final velocity squared is equal to 2 times the acceleration times distance. 0.762 times 9.8 times 2, and then take the square root of that, gives us this value instead for the final velocity. Now, again, on the formula on my right, which is the other, we can cancel out the other initial velocity term and just divide by 9.8 and get our time, which gives this. Multiplying that by our velocity of 3 meters per second means that on average, the ball would land 1.1830434635868 meters away. I lost my breath reciting that many precision digits. So if you don't want to write that many digits, that's why sig figs are useful. We round around to 2 significant figures. The one in the front counts, but we'll just round it to 2 decimal places just for clarity, because you can clearly write that down without taking lots of time. 1.18. We have 1.18. So this 1.18 is our average distance given kinematics. So we'll just write that down. Now let's verify using the measurements we've made and find the average. 0.9144 times 2, which is actually equal to 1 fathom. Add that to 1.1049 plus 1.016 plus 0.9652 and divided by 5 means that our average is 0.98298 meters. So we're a bit off with our measurements, and there are reasons for this, like the uncertain digits, or because it was hard, so we couldn't really get very precise measurements, maybe. Means a percentage error is 16.9491525423728, or to 2 significant figures, 17%. Which means we're a bit off, and that either means that we were a bit off with our measurements, or that the kinematics didn't really fit so well with our measurements. But it happens sometimes, and sometimes we just have a bit of uncertainty. This was actually a really fun experiment, so thank you for watching to the end.